the day here. This is the fourth year to talk about receiver performance and transceivers and all that in our world. So what's new for in the last year? And there's lots of options out there. So what's important in a contest environment? Well, it really comes down to hearing the weak stations amongst all the strong stations that are calling the same station too. And you'll find that you need a better receiver for the sideband contesters than CW. I'm sorry, I said that backwards. You need a better receiver on CW than you do on sideband, and I'll explain why. And you really need to be a good neighbor and have a clean signal. Of course, that came down to the contest ethics we talked about this morning. So we really have to share the band and make it more enjoyable for everyone. Receivers have been improving. Unfortunately, transmitters are kind of a mixed bag. We haven't seen a lot of improvement in that area. So what's most important, particularly in a CW contest, is what I'll call close-in dynamic range. It's something that I started pushing about 1976, and I'll explain what that means. And to figure out dynamic range, we have to know the noise floor of the receiver, and I'll explain how we do that. So sensitivity, that's been around a long time. Even if receiver designed in the 1940s, and certainly in the 50s, they talked about sensitivity. And that's, for sideband, it's a 10 dB, of course there was AM too, but for sideband it's a 10 dB signal plus noise to noise ratio. And while you measure that in the lab, you'll feed in a signal generator, and you'll adjust that generator so that when you tune the signal in and then you tune away from the signal and you put a voltmeter with a dB scale on it on the speaker, that difference between no signal with just receiver noise and the signal tuned in to a beat note that we can all hear, that's 10 dB, and that's what sensitivity has been defined as a long time. Now in the 70s, the ARRL started talking about noise floor and dynamic range, and those were new terms for the average amateur. And they defined noise floor as a 3 dB signal plus noise to noise ratio as opposed to 10. So let's listen to see what this sounds like. I'm going to play the little audio clip here and listen for the tone. This is going to be for sideband sensitivity. And that, you can hear the noise obviously in the tone. Now for CW, it's going to sound a little different. It's going to be, normally we use a 500 hertz bandwidth for CW, and it's only a 3 dB signal plus noise to noise, and so it's going to sound somewhat different. Now, other than a different pitch, the thing is you heard the signal was a little bit weaker, but since the bandwidth was less, it really didn't sound vastly that different. Now, we can talk about noise floor with any bandwidth, but normally if you look up something in QST, most of the time it's going to be 500 hertz. If you look on my website, nc0b.com, and go to the receiver test pages, that's mostly what we're using as a 500 hertz. So noise floor, though, is rarely a problem on HF, usually on 20 meters and below. Atmospheric noise, galactic noise, man-made noise, if most of us live in the city, that really predominates. But if we're in a rural location, we really want to know, okay, what do we need in the way of either sensitivity or noise floor? So I'm going to give an example here. I purchased 10 acres out in the middle of nowhere, east of Fort Collins, and so I'm going to give you some information on a 5-element, 15-meter Yagi at 70 feet. It's on its own tower. It's got 270 feet of a 7/8 hardline. And I pointed the antenna in the quietest direction. And this receiver measures with about no preamp on, a 0.5 microvolt sensitivity. And that's a pretty normal number. And you turn the preamp on, it measures about 0.2 of a microvolt. So we don't have some crazy numbers that we need. And the noise floor for CW 500 hertz is minus 135. So this is your typical receiver. And there's a picture of the antenna. You can see I don't have many neighbors. I only have a neighbor to the west, and otherwise it just looks like we're staring into space. and that antenna was sort of pointed to Europe, and that happened to be the quietest location, which really meant there wasn't much skip there. So most of you probably don't have a calibrated signal generator, and you say, well, gee, maybe I'm not working the DX I want. How do I know my receiver is performing up to what I need? So you can make some simple measurements if you just have an analog meter with a dB scale. Now you could, of course, use a digital meter, but they jump around and it's kind of hard to figure it out. But you can make the measurement. But I just say find a VOM that's got a dB scale on it and hook it up to your speaker. Or if you've got the line output on something like a more modern rig that has multiple outputs, use that. But we just need a normal meter. And so you're going to want to disconnect the antenna and then set the volume to read something on the meter at a reasonable level, let's say minus 10 dB. And you can put a dummy load on the transceiver if you want. That would be technically better. But it usually comes out with the same answer. Now we're going to connect the antenna and see how much the noise comes up. On a dead spot in the band, of course. So we want to know what is the noise gain when we connect the antenna. And you want to make this measurement with the preamp on and with the preamp off. So here's what I measured on 15 meters with the preamp off. The noise only went up 3 dB. Now that's not enough. Just like when we measure noise floor and we tune in a signal and we get a 3 dB difference between the signal tuned in and the signal out of the passband, that means the signal equals the noise floor. Well, here when we're connecting the antenna, if the noise goes up 3 dB, then your receiver is equal in noise to what's coming in on the antenna. Well, that would mean the receiver has some impact. We don't want the receiver to be just barely good enough. We turn on the preamp in this case, and the noise went up a little over 8 dB, and that's plenty good. Some might argue 6 is okay. I think closer to 8 is probably what you want to shoot for, but that means the receiver is not going to be limiting what you can hear. Now the interesting thing is, okay, we've got the preamp on. Let's rotate this antenna around if we're lucky enough to have a guiding and see how much difference there is. Now, a couple weeks ago when I was remeasuring these numbers, which I'd done a year ago, I got a 13 dB difference on 15 meters that day between where towards the southeast, where there was skip towards South America or Caribbean, and sort of towards the north. So sometimes the noise is really way more significant than what you measure in the quietest direction, and usually is. I wanted to do the same experiment on 10 meters, so I also wanted to try a different transceiver. So I've got the previous one was an ICOM 781. It's 25 years old, and then a Pro 3. It's a couple years old. And so in this case, I had a 5-element monobander on 10 on its own tower at 65 feet, and then the 5-element 15 at 70 feet. And you can see with this rig, the difference on 15 with no preamp was 4 dB, but on 10 it was 3. And again, 3 dB means the receiver has as much noise as what's coming in on the antenna. That's not enough. But then we go to preamp 1. Oh, we're way big numbers, more than 11 dB, more than 9 dB. So that's plenty adequate. I've never heard on HF anyway a case in this case where the second preamp on my Pro 3 lets me copy a signal I couldn't copy with preamp 1. Maybe 6 meters, but anyway, at HF, if you've got numbers there in the 10 dB range, there's really no reason to be turned on preamp 2. It just make the chance of overload more likely. Now there's more variables, unfortunately, and I had to learn this the hard way. Depending on our lot size. When I'm in Denver, I have a 62-foot by 120-foot lot, and I put my tower where I could put it. But out here in the country, I put some of the towers further away than others, and I found out a lot of noise generated in your house. Now, if there's a big contest, I tell the wife to stay in Denver and I turn everything off. But things that make noise, we unfortunately have a Sony TVs with CRTs. They won't die, so they haven't been replaced. Plasma TVs, of course, make racket. I have a UPS on the computer, and that makes a racket, and a broadband router that makes birdies. And wall warts. Most everything today has some sort of little transformer. They used to just be transformers. So now they're switching power supplies, and they put out birdies all over the place, so that makes racket. And of course, maybe the worst thing is one of those hand touch lamps. I used to have one of those, and it didn't make the move. It somehow got lost in the trash. So here's the QTH out east of Fort Collins, and as you can see there's a tower there right by the garage, and there's also one there on the far right that's near our bedroom, and those are too close to the house, unfortunately. The rest of the towers are 200 to 350 feet away, and the difference is astounding. The one here on the closest one on the left, that's the 10-meter tower, and the one farthest on the right, has a little 3-element 10-meter, and the noise difference I've just stunned. The 5 elements is nice, but the difference in my case was vastly quieter. So think about it where you put your towers, if you've got the space, and maybe you have to worry about the neighbors. So I'm going to get as far as I can from my house, but I don't want to be right next to the neighbor's house too. So that's something you have to be thinking about. So from a noise floor standpoint, here was a list of the top 10 receivers or transceivers. Actually, the only receivers there is the Perseus. What's the noise floor? You can see they're fairly similar. If you are using Perseus for a skimmer, you're probably going to want a preamp because that's been on the low side. But I put the Drake R4C down there at the bottom as a comparison, minus 138 dBm, and the Elecraft's minus 138 dBm. So guess what? Nothing has changed for a long time. Receivers are adequately sensitive, and we really want to we don't want to be throwing preamps in when we don't need it. So dynamic range, what is it? It's a number in dB dealing with the weak signals that we want to hear. At the same time, the band's cluttered with signals 30, 40 over 9. So it's trying to deal with this multiple signals. You know, if there's 2 guys on the band, we don't have a problem. But that's not what goes on in a contest, of course. So what's close in dynamic range? What's wide space dynamic range? And why does CW operators need the better receiver? It's certainly not unimportant on sideband, but we need about another 10 dB on CW. So when we're going to measure dynamic range, it really is talking about third order distortion. That's in band. It's close to where the signals are. And this is what the league defined back in the 70s. And they started testing receivers with just 20 kc spacing, 2 signal generators 20 kcs apart. And that was a reasonable choice. Back then, in the early 70s, well, most of the receivers would have been made in the 60s and early 70s, so it worked okay. But we know where the distortion products are. And the definition was we feed in 2 signals, and as we up the signals, we start hearing the third order product. Just like we look at a transmit 2-tone test on transmitters, you can see the distortion products. Well, the same thing's happening in the receiver. So we know exactly where to look for them. If we have 2 signals 20 kilohertz apart, the third order product is 20 kilohertz above the high one and 20 kilohertz below the low one. If it's a 2 kc test, which I started testing in 76, it's 2 kilohertz above the high one and 2 kilohertz below the low one. So we don't have to go looking for it. We know exactly where to tune it in and try to measure this. The trouble was receivers started changing in their architecture, and up conversion became the way to get rid of preselectors and mechanical stuff. And for 20 or 25 years, almost every transceiver that was up conversion, or even some receivers, in this case the R4C, which started all this because I bought an R4C, and it was tested in QST, and they said it was great, and I used it in a 160-meter contest, and it was terrible. So the receiver is what it was, so the test obviously wasn't testing what reality was. So if we have 2 signals that are 20 kilohertz apart, and we tune in the third order product, in this case on the high side, then the roofing filter, the first IF filter, and all these up conversion radios for like 25 years, well, the filter is going to reject the close-in signal some, and that's 20 kilohertz away, and the filter is plus or minus 7.5. But the one that's 40 kilohertz away is hardly going to get through the radio at all. So therefore, we were only testing the front end, the first mixer. If the preamp was turned off, nothing but the first mixer. And if it had a preamp on all the time, well, then it tested 2 stages. Well, that isn't how we, in a contest, the guy up the band 40 kcs isn't the problem. So in the case of the Drake, I said, well, I've got to test the whole radio. So I squeezed the signals close enough. In that case, it was so it would test a filter that radio that had a 8 kc filter in the first IF. And that, of course, worked with the 15s, too. So in that case, we were testing clear downstream, and that's why the numbers were so different between 20 kc, which maybe was 90, and 2 kcs, which was maybe 70 or less. So the simplest way to get higher performance is to have a band mode appropriate filter right after the first mixer. And of course, some radios are designed that way. A TR4, what's it got? First mixer, 9 megahertz filter, it's 2.1 kilohertz wide. So if you do that, well then you've knocked out maybe 95% of the stations on the band by getting a filter for sideband that's between 2.4 and 3 kilohertz. And on CW, say 500 hertz, 1 kilohertz, something like that. And then everything downstream doesn't have to work so hard. So what's changed in the last 8 years? Well, we had upconversion radios for about 20 or 25 years, and then Ten-Tec came out with the Orion, and that was in 2003, and they went back to like the TR4. First IF was 9 megahertz. And then Elecraft followed, and now Yaesu with the FTDX 5000 came along, and now the Kenwood with the TS590S. So it's interesting, at the moment, ICOM's the only one that hasn't offered that as an option. And you can produce good numbers, but it's more difficult and more expensive with the upconversion approach. So it'll be interesting to see tomorrow, if we show up at the Kenwood booth, the 590's been a good seller, and will they offer like a glimpse of some $4,000 radio that would be full featured? I don't know. But it's nice to see competition, and Kenwood's back in the battle again. So when are two out-of-passband signals a problem? So you say, okay, dBm, I don't relate to that too much. So let's just talk about S units, what it reads on the S meter. Let's assume our S meter reads properly, S9's 50 microvolts. If we're in a contest, we really want the preamp off most all the time. We're in a potential overload situation. So no preamp, typical noise floor, minus 128 dBm, 500 hertz filter, we're talking CW. And let's say we look up, pull out the QST, or we go on the website and we look up with all that wonderful data that's there in PDF form. We want to know, okay, I own whatever radio I have. Say it's an FT2000. It's got a 60 dB dynamic range. Well, it's about 61 or 62, but it's about 60. So at S9 plus 5, you're going to start overloading that radio. And you hop up a bit. Let's look at the Pro 3. That's about 75. So the signals have to be 20 over 9 before you'll start to have a problem. And then we can go up to, well, let's say the Orion 2, that's 95. Well, we're talking about 40 over 9 before we start having an issue with the dynamic range. So it kind of gives you a feel for when it's likely to be a problem. And the distortion products in the receiver, they're like not a problem, and then they get to be a problem in a hurry. Because as the signals go up, the signal goes up 5 dB, and the receiver is an overload. Well, the intermod, which is creating QRM that isn't really there, goes up 3 times that amount. So if the signal went up 5, the intermod went up 15 approximately. So we want to stay out of that. So here's the top 8 transceivers, 2KC test, and we range from 101 with the 5000. And we go down from there in my list, which is all sorted by the 2KC. And the interesting thing is the new Kenwood is a mixed bag. It's a down conversion radio, or in other words, a low frequency IF, on 160, 80, 40, 20, and 15. But it's an up conversion radio on the work bands and 10 and 6 meters. So it's got 2 different listings, 88 dB in one case and 76 in the other. And the 76 was kind of typical, a little bit higher than the standard. Most radios for about 25 years were about 70, so a little above that. So it'll be interesting to see when you guys start using, if you use that radio, and there's a de-expedition. Obviously you're not going to have, except for 10 meters, they won't be a case of a contest, but we get, Peter 1. Everybody wanted to work them on the work bands too. So if we get a massive pileup, well then, it's interesting to see how it plays out for that one. So how did the new rigs perform on CW? And I was very lucky. I was able to borrow an FTDX 5000 from Richie, W1STT. He's somewhere in the audience here. I borrowed the Kenwood from Ken, a W3JK, and Ten-Tec loaned me the Eagle. And I used them in this past season's 160-meter CW contest, and going back and forth. But I have 2 stations set up so I can change rigs by just changing chairs. And really, they all perform very well. They all have numbers, in this case 88 or better, and so overload wasn't an issue. Of course, the feature differences are not, it has to be expected. I mean, the one case we have a $5,000 radio, another case like an $1,800 radio. So I'm not trying to say they're identical, but from the standpoint of just, in this case, I was working S&P, trying to dig them out to start at one end of the band and work up 60 or 70 kilohertz and then start over. I didn't find the receiver folded up. It was important to have the narrow bandwidths that we're now spoiled with DSP. I could crank it down, and I really did need the narrow bandwidths, at least in the S&P mode. So it was interesting. I used those 3 rigs over, well, basically about 3 months. And in all 3 of those contests, the ARRL 160, the W1BB Stu Perry contest, and the CQ 160, I worked CE1/K7AC in all 3 contests. And I had to have that narrow bandwidth because he was fairly weak. And strangest thing, I'd give him a call, and I wanted to hear when he was transmitting back to me, but people were still calling him. So it was like he was being QRM by the guys that didn't figure out he was trying to transmit. So I had to go down to that 50 hertz in the case of the Kenwood and the Yaesu, or the 100 hertz in the case of the Tentec, to make the contact. Luckily, when the de-expeditions come around, a lot of them run split, of course, but they don't do that much on 160. So in that case, at least you can hear when the guys come back to you without so much trouble. But I really needed those narrow bandwidths. Now, here's one thing to take away from you. That whatever the dynamic range of your radio is, it's not fixed as to where you've placed it. You can turn your attenuator on, or you have your preamp on if you really need it. But you can move that dynamic range window around. If it's only 70 dB, well then run your attenuator. Like on 160, when I talked about the 3 dB difference between a signal peaking up 3 dB makes it equal to noise floor, I can run a 20 dB attenuator on my transmit antenna on 160 and still get an 8 dB peak above the noise floor. So I typically run on 160 a 6, a 10, or a 12, depending on which rig I'm running. And so I'm taking that dynamic range, whatever it is, and maximizing it. So you want to be able to utilize that attenuator when appropriate, and particularly on sideband. If the band noise is reading S6, there's no point in that. Punch in the attenuator until it goes down to S2, S1, because that's just running on band noise, and that gets you nothing. You give up absolutely nothing if you just bring the S meter down towards S1. Now let's look at the transmitters. I'm now testing the transmitters besides with a two-tone test with white noise. And you feed in white noise in the mic jack to better approximate speech, and we can kind of get a better idea what's really going on, and call it a 1,000 tone test instead of a two-tone test. Though this slide, if you've been here before, you've seen this one before. This was from W6XX, and he has both a Mark V that he can run in Class A and a K3 that runs in Class B, and they both can put out the 75 watts needed to drive his 8877 linear. And so in Class B, by feeding white noise in the mic jack, we have to go 6 kilohertz away from the edge of his signal, to be down 60 dB. In the K3 case, because that's Class B, and that's sort of typical. But if it's Class A, 1.5 kilohertz away, you're 60 dB down. Now, wouldn't it be nice if everybody was that clean? But unfortunately, they're not. So these are the rigs that shipped this since last Dayton, and so I've tested all those. Here was the Eagle, and I fed in the noise, and I had to go 7 kilohertz away to get 60 dB down. And I just assumed that that was a little cleaner than that. In the Kenwood, again, this is Class B, I had to go 5 kilohertz away to get 60 dB down. Now you're saying, okay, what does this mean? Well, if you're trying to work, the guy's calling CQ, 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 and he's running, obviously. Sure, I want to work that guy 3 kcs away, but if towards the end of the contest, if he's just incessantly calling CQ, it's going to be really hard if he's 40 over 9 for me to work the guy that's S2 because of his transmitted sidebands. And this isn't splatter like he's overdriving his amplifier, hopefully. This is just what's coming out of the rig. The other rig that I got to use a little earlier in the year, a friend of mine has a 7600, and he said, 2 of us in this group every week get on the air, and they were complaining that the opposite sideband suppression wasn't good. And I thought, well, that doesn't make any sense. So he sent it out to me, and strangely enough, when I compared the distortion products of my Pro 3 to the 7600, it was about 10 dB worse, and that was really surprising. I don't know why that happened, but Adam Farson, VA70J, he also got about the same measurement. So that was a surprise. So I offset these two so you could see them. So the top is like 8 dB difference, and then off to the side the 18 dB difference. So you can see the 10 dB difference approximately there. Now here was the FTDX 5000, and in Class A, that's the bottom trace. And in this case, somewhat similar to the Mark V, you only had to be 2 kilohertz away to be 60 dB down. And just look how straight edge that passband is. But the unfortunate thing is, when you started hitting the ALC, it drastically reduced. The quality of the distortion product went way up. And that was with the meter reading half scale. And half scale is only 3 dB in that case. So going from no ALC to half-scale ALC, you can see that the value of the Class A went away. This can be fixed, but I don't know whether it's a hardware problem or a firmware problem, but hopefully Yaesu will fix that. Now, decades ago, Collins said, ALC is just a leveling circuit. We shouldn't be trying to process with our ALC. It should have a slow decay. And of course, way back then, we didn't really even have processors, but today we do. But the processing should be done early on, and then the ALC just keep things under control. So I was on the air with Ritchie's 5000, and I had my Alpha 89, which is a pair of 3CX 800s, and I was talking to my friend Pete, I think, and a guy broke in and says, I want to comment on your signal. I thought, oh my God. How many people jump on your frequency that are maybe pissed off about something? So he said, I've recently purchased a P3 for my K3. That's a band scope. And he says, you have the cleanest signal I've ever seen on the air. I was running no processing and no ALC, and it was just phenomenal. So this problem with the 5000 could be fixed. One would hope it will be. Yes? Well, last year, if you were here, I had that information. Pete did the test with his 8877, which is one of the better amplifiers. I mean, better tubes. It happened to be a homebrew amp, but there's plenty of rigs out there, Alpha and others, that have 8877s. And the third order was only degraded 2 dB. Now, in the case of the Mark V, in Class A, the fifth order is down like 70 dB, and the seventh order, you couldn't even see it. That was degraded by the amplifier, but they were still way down. So the third order, very slight degradation, let's say 2 to 3 dB. So, and I was very happy to see the triodes in the Alpha 89 were obviously not degrading it significantly because the guy was just ecstatic how it looked with the P3. Now, certainly, if you tune the linear wrong, all bets are off. I don't think the 3500Zs are quite as clean, but I had a pair of 3500Zs in TL922, and that was relatively clean as long as I loaded it up properly. But that's an issue for sure. Now, if you've got your knob set to 11, like Doug was talking about, that's a different story. So. But some guys like to have elbow room. Can you imagine that? And they like that 10 kC transmitted signal, and hopefully somebody chases them off. But that really comes back to the contest ethics, that we really should all be competing with the cleanest signal that we can put out. So let's go back to go from sideband back to CW signals and see how this compares as far as like how close can we work to signals. You know, if we're going to run, hopefully two guys that are really big signals are going to slide a little bit apart, but we want to work that mult or whatever it is we're looking for. So I said, okay, let's test some transmitter and see what the keying sidebands are. I mean, if we just put a key down in the dead carry, we don't have any bandwidth to speak at all, but hopefully we're sending our call and a report, and it's the keying, of course, that makes the sideband. So I said, let's just measure this with two rigs. So I'm going to receive with a K3 with a 400 hertz roofing filter and a 400 hertz DSP bandwidth, and I decided to use an Omni 7 as the transmitter because it's got a real easily adjustable rise and fall time. Just bring up the menu and turn the knob. So I set the transmitter to read 40/9 on the receiver by using attenuators and all that. And this S meter was astoundingly accurate. I checked the calibration. It was wonderful on this K3. And so then I put the Omni 700 hertz away and then let it just turn the keyer on 30 words a minute going did. When you set the rise and fall time to 3 milliseconds, which was the fastest, the signal was S7 from the keying sidebands. If I set it at 6 milliseconds, which was the default from the factory, it went 2 S units less and dropped clear down to S5. If I slowed it clear down to 10 milliseconds, it went clear down to S3. So that was over a 20 dB difference at 700 hertz away on just what the keying sidebands were like. Of course, I had to do it with test equipment too. But so here was the 10 millisecond, pretty clean. Bandwidth about 900 hertz at 70 dB down, 70. And here was the 3 milliseconds. Well, that looks a lot different. And it was 1500 hertz wide at 70 dB down. So let's superimpose the two. So you can see not only did it was worse, but look how it keeps going. And it ran off the scale of the scope where the 3 millisecond was causing the keying sidebands. And of course, we know there's rigs worse than that. Tom Rouse has been complaining about the FT1000 series for decades, and he fixed it for like $2, but it had, who knows, a 1 millisecond rise time. I don't know. I know K0RF that lives about 50 miles from me now. He used to live about 30 miles from me. I moved. His keying sideband drove me nuts. I couldn't get within 4 kilohertz of it. So here we measured it on the spectrum analyzer. We got 20 dB, and was using 2 transceivers. I got 22. So you see the numbers are right. Now the question is, how soft is too soft? Probably 10 milliseconds. You guys are going to think that's a little soft, but don't set it at 3. Now, if you don't have a spectrum analyzer, which you probably don't, well, you can look at it on a scope. Hopefully you have a scope. On the left there's the 3 milliseconds. You see how it ramps up fairly quickly. And then the 10 milliseconds, like in this case, it's almost a 45-degree angle. So it's the ramp up that causes the key clicks and all those sidebands. So just the facts. On sideband, we'd really like to have 70 dB or more dynamic range, and that makes sense. For 25 years, all we had was up-conversion radios with about 70 dB, plus or minus some, but they were pretty much the same. And on CW, you really wanted 80 or more, and even W8JI have been agreeing with that for decades. That's fine. I mean, we'd all like bigger numbers, but this is what should be kind of considered the minimum. It's easiest to do with what we call down conversion radio. That's not exactly right, but up conversion was up. We understand that. But if you have a transceiver with a 9 meg IF, well, if you're on 160, it's up converting. But that isn't the way we're using the term now. That up conversion, down conversion is just mean down conversion is low IFs in the 5 to 11 megahertz range, and up conversion is something 40 to 50 to 70 megahertz. So here's some numbers of what we see available. Clear back in 2001, we had 80 dB with the Omni 6. The ICOM, the Orion came along and bumped it up into the 90s. The Flex came along, and they've got some good numbers. Now, I ask this every time I give a talk. How many people here are using Flex in your contest situation? Would you raise your hand? 1, 2. And I talked to Gerald about that. And what is it? Is it the ergonomics? Is it losing focus with N1MM or whatever? No, there aren't too many Flex users in the contesting world. And be interesting to get feedback on those of you who are using it. are you completely happy with it? And most are still using the classic radio. So that's something I'm not totally clear on. I know that Gerald would like to know the answer to that. The K3 95, and it was if you narrow the bandwidth a bit on the K3, you can actually get up to the same 101 number that you could on the 5000. But so we've got several radios here that have numbers that are completely adequate. Here's a list of kind of what we've seen over years. Of course, the K2 came out, and that started their march into the K3. The funny thing is, there's the R390A, which goes back to the Korean War, at 79 dB. And of course, some people really like that, and I know SWLs do. But so we've had some good numbers for a long time. The Pro 2, Pro 3 in the mid-70s. We've got an FT2000 down there in the low 60s, and that's the surprise that a radio would come out that's that bad in the last 10 years. The R4C down there, that's where I started putting a roofing filter in the R4C in 1976 because it tested good, but it didn't play well. Well, the answer was take out that 8 kC filter, put in a 600 hertz filter. So it was 58, below 60, and it went up to 83, above 80. So that fit in my scheme. So that's what started me testing radios. I mean, I'll clear back in 76, I didn't say, I think I want to be testing radios until 2011. I just started doing it because the radio I bought didn't work. At the bottom of the list, there's the VR5000, and the league tested that, and I tested it for Passport, and they tested it for QST. And for me, it was the worst radio I'd ever tested, and the league said it wasn't a contest radio. So I guess we agreed on that. Now, here's one thing that the league and I are in disagreement on now. Most transceivers are phase noise limited today, close in. In the older days, we had a PTO and a band crystal, and we didn't have much in the way of noise. Now, the radios weren't as good as today, but it wasn't a noise issue. And as things started improving, almost every test in QST came up phase noise limited. And you look at my chart, came up phase noise limited. So the engineers said, well, we want to know the number. So there must be some way to measure third order intermod distortion product that's covered up with noise, and you can do that. So they used a spectrum analyzer with a 3 hertz filter, and as you go down from 500 hertz to 3 hertz, you drop the noise about 20 dB. So in order to test now, what the league does is they measure the noise floor of a transceiver the normal way, and then we have to feed in a third signal at that level. So this is a spectrum analyzer plot with a 3 hertz bandwidth that's able to drop the noise, the phase noise, somewhere in the range of 20 dB, so that we can see that distortion product. So you adjust the 2 tones that are for our test so that the intermod product for the dynamic range test is the same blip height as the reference tone. Now, how many people use a 3 hertz filter in a contest? Raise your hand. So far, no one's ever said yes. So what did this net us? If you measure, this just happened to be the radio I was testing it with. I measured 78 dB, which is fine, at 2 kilohertz, the old way, the way the league used to do it and the way I still do it. But then I measured the new way, and it went up 9 dB. It went up to 87. It's the same radio, but unfortunately, it's just a measurement difference. The measurement isn't wrong, but the question is, you can't hear that. What you're seeing on that picture, you can't hear that because you don't have a 3 hertz filter in your ear. So the old method was whatever degraded 3 dB, that was a dynamic range. If it was a distortion product, a third order, that's what it was. If it was phase noise, that's what it was. So let me play just a little audio clip here. It will sound very much virtually identical to when we were measuring noise floor before. It's just the third order tone and the noise, and that was dynamic range. So you could hopefully hear the tone. You weren't in a dead spot where there was a null. And so if it, in this case, either the tone went up 3 dB or the phase noise went up 3 dB, and that was it. Now, since they're using the 3 hertz filter, they're able to see that, but in this case, when I measured this rig, the noise coming out the speaker, the noise measured on the RMS meter, the noise went up 10 dB, but I could hear absolutely no tone. And what did that sound like? Just noise. So they're not really the same test. And I don't know what the resolution is. I went round and around, and they say, well, we want to measure the distortion product, but I say, okay, until we're running 3 hertz filters, what's it prove? So we're just not on the same page. I think they didn't like publishing that virtually every radio was phase noise limited. And then if you measure it this way, the numbers are bigger. Now, if we went back and measured, let's say we took a Collins S line and measured it with the new method and the old method, it would be exactly the same answer because there's no phase noise. So it isn't a number that's wrong, but it just doesn't apply to anything. And also, everybody likes to say their numbers are bigger. And so if we can say it's 90 dB and not 80 dB, well, sounds good. I didn't catch on to this for a while, though, because in 2006, I owned a 7800. Well, actually, a little bit later than I did, but the 7800 was tested, and this just happens to be something that was tested 1 year apart, so that's just why I picked it as an example. And the league published 80 dB at 2 kilohertz and 67 dB at 1 kilohertz. That was the original 7800. Then they improved it at 1 kilohertz drastically by changing the LO. They've also put in the 3 kilohertz proofing filter, and that's the one I owned. And then the league measured it again, and they got 86. And the previous year, they got it 80. Well, I had 1, 2, and I got 80. So, but I didn't know why that was. And they didn't happen to publish measurement at 1 kilohertz. So I didn't catch on for a while. But then we started getting more and more numbers that my numbers on my website didn't jibe. And people were calling me up, what's going on here? So I finally found out. And here's an example with the Flex 3000. Gerald Youngblood says it's a 90 dB radio, and that's what they publish, and that's the way it comes out. It's phase noise limited, but if you look at what's in QST, it's between 95 and 99, depending on different spacings. And the funny thing is, in this case, what Flex publishes for the 5000, which is a more expensive, better radio than the 3000, but if you compare the numbers published in QST, the 3000 looks like it's better than the 5000, but the test method changed. So now we know we can't compare anything 2006 and older to 2007 and newer. And on top of that, the Orion 2 and the K3, for instance, look like they're not as good as the 3000 because the 3000 can come up looking like 99 dB. So that's a problem. I don't know if there's going to be a resolution to it. I'm not going to change my testing method because I want to compare stuff for the last 30 years. The league does publish reciprocal mixing. There is one number in there amongst the typical reviews, like 2 pages long. There's all sorts of great data in there. And reciprocal mixing is listed, and that's what phase noise is. But it's not much attention paid to it and not much explained about it and certainly not much data to compare. So the difficulty is, well, it looks like a Flex 3000 is better than a K3. And I don't think you guys that run the contest would agree with that. So how good's good enough? 70 dB minimum for sideband, 80 dB minimum for CW. We'd like to have a safety factor, so let's say 90 dB. We'd all love to have that number, and okay, that Kenwood is an 88, that's fine. We don't need crazy sensitivities because we really want to keep the preamp off, certainly on 40 meters. If you've got the preamp on at 40 meters, unless you're using a beverage, a loop, maybe one of those pennants or those unusual receiving antennas, well, that's a different story. But if you're using your transmit antenna, keep the gain down, use the attenuator when you can. Yeah. Okay, the K3 with the 200 hertz roofing filter and the 200 hertz DSP tests out at like 101. If it's a 500 hertz bandwidth in the K3, it's 95. The flex, by the way, flex measurements is 90, and the way I measure it is 90. But with the new method, it looks like the Flex 3000 is better than the K3, and it's not.
Okay.
All right. Oh, good deal.
So a couple of things. Thank you very much, Rob. I appreciate all the hard work that goes into that. Ray Novak, are you here? Ray from ICOM. Nice round of applause for ICOM and Ray Novak, N9JA.
I want to thank everybody for coming out, irregardless of what equipment